Now, last but not least, oftentimes you may find yourself dealing with a data set, for example, images, where your vectors, let's say each vector point here will be an image, so the vector, the D here, would be very, very large, perhaps 1,000,000, right? Then the covariance matrix, which involves the outer product of these vectors here, would also be 1,000,000. So we're talking about a matrix itself, which is 1,000,000 by 1,000,000. You will have trouble storing this in memory in your computer, much less doing a full eigendecomposition, right? Nonetheless, we do PCA on signals and images that are very high dimensions routinely. And so there is a simple trick that we can use to do this. So the solution is to see the trick, let's look at an alternative problem, right? Let's look at this eigenvalue, eigenvector problem here, where now my C matrix here will be a matrix of inner products. So in other words, let me put the data set that I have and organize into a big matrix, which I'll call capital X here, right? Which will be a matrix where each of the columns here is the data set. So if I have n points here, I'll have n vectors, right? And my matrix will be D by n. So X transpose times X here now will be a matrix of n by n. So this vectors ui here that also necessarily have size n, right? So let's look at this eigenvalue problem. So, and plugging MC here, the definition we chose to use, we can see that this is true. And we take this here and multiply by X on both sides. So we'll end up with here X times X transpose, which if we do a simple analysis, you'll recognize this as my original covariance matrix, sample covariance matrix S, right? And this will be true. In fact, I would have to have a 1 over n here, or essentially a scaled version of the eigenvalues. But then in the case, this will be a S. And so in other words, if I call this vector here Vi instead of Ui, then I have my original eigenvector, eigenvalue composition in terms of S, right? So the point being here that if Ui is the eigenvector of this other alternative problem here that we stated, then X, and I compute the eigenvector composition of C vector here, this C matrix here, then once I have this U, all I have to do is multiply U by X, and I'll obtain the original eigenvectors of S itself, right? So why does this help? Let's say you have 1,000,000 dimensions for D, but let's say you only have 1,000 points, so this matrix here will be 1,000 by 1,000, which is easier to deal with than a matrix which is 1,000,000 by 1,000,000. And you can do the eigendecomposition of a matrix 1,000 by 1,000 using this trick here. And to obtain, so you obtain eigenvectors which are 1,000 dimensions, but to obtain the one back in 1,000,000, you multiply by your data matrix X. So this is a popular trick that people use whenever they're stuck processing, doing eigendecomposition or PCA procedures on data sets where each data point is very high dimension, for example, images of high resolution.